Hi everyone, I'm Navid, and I'm very excited today to be talking about our work on Diva, a dynamic range filter for variable length keys and queries. This is joint work with some wonderful colleagues at the KTH Royal Institute of Technology, and we were lucky enough to win a Best Paper Award for it at VLDB 25, so I'm very excited to be sharing our results with you. Okay, so let's start with what a filter is. A filter is a compact probabilistic data structure that approximates a set of keys. We can give the filter a key X and ask if it exists in the set or not. Because filters are compact, they're oftentimes stored in small but fast memory, so things like DRAM, and they approximate large sets of keys that are typically stored on slower but more abundant media, so media like SSDs and disks. If the key X that we give the filter actually exists in the set, the filter is guaranteed to return a true positive to us, telling us to go and fetch it from disk. And if the key doesn't exist, well, the filter is most probably going to return a true negative to us, telling us to avoid doing a redundant access to disk for a non-existent key. Sometimes, though, the filter might make a mistake, and it might return a false positive to us, telling us to go and access the disk anyways. The probability of this event happening is known as the filter's false positive rate, which is usually denoted by epsilon. This false positive rate is tunable. The more memory we give the filter, the lower we can drive the false positive rate. Now, because filters return true negatives most of the time for non-existent keys, they're used in all of computer science to save storage accesses and network hops, yielding massive speed improvements. So traditional filters are amazing. We love them. But they have one core limitation, in that they can only support point queries. So we can only give them a single key and ask if it exists or not. A natural question, especially in the context of a database system, is, okay, what if I have a range of keys that I'm interested in? What if I want to know, is there anything in my set that is included within the range from A to B, let's say? A data structure that answers this query with the same sort of semantics as a classic filter is known as a range filter. So we want no false negatives, and we want a low and tunable false positive rate. These range filters have applications in many different domains as well. The killer application really is within the context of an LSM tree. An LSM tree is an on-disk data structure widely used to implement write-optimized key value stores. The core idea is simple. An LSM tree heavily amortizes the cost of writes to disk over many insertions by buffering insertions in memory and only doing IOs once that buffer fills up. It flushes the buffer to create a small sorted file on disk. By doing so, it creates a list of chronologically ordered files, and it also periodically merges the oldest files together to create larger and larger files. So what we end up with is this hierarchical looking structure that, well, the top levels have the smallest files with the most recently inserted keys. And as we go down the hierarchy, we get exponentially larger files with older and older keys. Now, an LSM tree is amazing for writes because it heavily amortizes the cost of writes, but it's less than ideal when you want to do range queries. Because we don't know which of those files contains relevant data to our range query, we have to search every single one of them, potentially incurring many IOs. This is where range filters come in. If we store a range filter for every one of those files in memory, we're able to consult the filter before accessing the file to see if that file has relevant data. If the filter returns a negative, then we can safely skip over those files and win massive performance boosts by doing so. Okay, so that's all well and good. So the core question becomes, how do we actually implement a range filter? As a strawman solution, one might consider using a standard point filter to do range filtering. So you might consider using a traditional Bloom filter, and the idea would basically be, we're going to issue a subquery for every single one of the keys that we have in the range that we're interested in. If all of those subqueries return negative, we know that the range is empty, but if at least one of them returns a positive, then the overall outcome becomes a positive. So this approach works, but it has three core problems. The first problem is that, well, first of all, the query cost actually is very, very high. This is because we're issuing one subquery for every key in the range, meaning that the query cost is actually linear in the length of the range, which might be huge. The second problem is that this approach actually has a higher false positive rate than what you would usually expect. In particular, if we start with a false positive rate of epsilon and we issue our subqueries, what's going to happen is we can show by a union bound that the false positive rate is going to be r times higher than the base false positive rate that we started with. It's going to be epsilon times r. This effectively means that the filter is going to be useless when we have long range queries, because the false positive rate is going to be driven all the way up to 1, and, well, we're simply going to return true for every single query, irrespective of what the query actually is. Now, granted, you might be wondering that, well, maybe we're able to give the filter more memory to compensate for that added factor of r and reduce the false positive rate. But turns out, to do that, we actually need to give the filter log base 2 of r extra bits per key to keep the false positive rate stable. And this requires us to know what the value of r is at construction time, or at least we have to know some upper bound on the maximum range query length at construction time. This information isn't typically something that people know, so this approach doesn't really translate to many practical scenarios. The third problem is actually much more severe than the other two. The issue is, well, this entire approach breaks down immediately the moment we have to do range filtering over an infinite universe of keys. So for example, if we're interested in string keys, any range we pick in the universe of strings is actually going to include infinitely many possible keys within it. So we can't even begin to enumerate these keys and issue a subquery for each. So we're sort of stuck. To recap, we have 4 problems. The first is a high query cost, a high false positive rate, and being stuck with bounded queries and fixed length keys. So the question is, how much can we improve these? Ideally, we would like to have a constant time query cost. We would like to have a false positive rate that looks like epsilon, and we would like to support variable length queries and variable length keys. In addition, we would like to support dynamic operations as well. We want to be able to maintain the filter as new insertions are made to the data and old data is deleted. Range filtering has been a hot research topic in the past decade, garnering interest from both the theory community and the practical community. But what's interesting is that if we look at these papers and we consider those 5 goals that we talked about, we see that actually only 3 of these approaches support fast queries, only 5 give you some sort of a false positive rate guarantee, only 3 support variable length queries, only 1 supports variable length keys actually, and only 1 is dynamic. That is to say that none of these filters attain all of those goals simultaneously. So a natural question is, can we design a range filter that attains these goals simultaneously? The unfortunate reality though is that this is impossible. So in some sense I was being a little bit unfair to the other baselines. And the reason why this is impossible is due to this theorem from back in 2014. It states that if you want to design a range filter with a worst case false positive rate guarantee, you would have to spend log of r over epsilon bits per key in terms of memory. To remind you, r is the maximum range query length we want to support, and epsilon is the false positive rate we want to achieve with our filter. In particular, when we want to support variable length queries and variable length keys, the value of r is basically infinite. The reason is, for variable length queries, well, we can just make the range query arbitrarily long. And for variable length keys, any range we pick is going to include infinitely many keys. So if we take this value of r and plug it into the lower bound expression, we get that our memory has to be infinite, which is a bit of a strange statement. All of these weird things are happening because we're trying to guarantee a false positive rate bound for the worst case scenario. We sidestep these issues and we design around it by considering what would happen in the common case that people care about in practice. In particular, we consider datasets that come from smooth-looking distributions. We'll get to what that means soon. So, by designing around the lower bound, we designed the first dynamic and fast range filter for variable length keys and queries that provides a false positive rate guarantee for the common case that we care about. We dubbed this range filter Diva. So let's get into how it works. So the core technique and the core idea of Diva is to dump the single most widely used primitive of filtering, which is hashing. Right from the get-go, we're not going to use any sort of hashing, and we're simply going to store the keys lexicographically from A to Z. What this is going to allow us to do is, given a range query, we simply have to find the successor of the left endpoint. This is the smallest key in our dataset that is larger than the left endpoint. By comparing the successor to the right endpoint, we have basically 2 cases. If the successor is smaller than the right endpoint, then the range query is for sure non-empty. And if the successor is larger than the right endpoint, then the range query is for sure empty. So based on the successor alone, we're able to answer the range query. So the only thing that we require actually to implement this query plan is to support fast successor search over a compressed representation of our keys. Diva does this by leveraging the dataset's distribution. Here I'm showing you the cumulative distribution function, or the CDF for short, over the key space. You can think of this as basically the slopey parts representing dense regions of the key space, and the plateaus representing the sparse regions of the key space. Intuitively, because the sparse regions are sparse, we need to store very few bits to be able to differentiate the keys in those regions. So we're able to truncate the keys in those regions more. And, well, because the dense regions have more keys within them, we have to store more bits from each key to be able to differentiate them. So we have to truncate less from those keys. Diva implements this intuitive idea by approximating the dataset's distribution and leveraging that to decide how much to truncate. The idea is it's going to sample every 1,000th key in the dataset, and it's going to connect these samples with straight lines. This is going to give us a piecewise linear curve that closely resembles the underlying CDF. We actually picked every 1,000th key as a sample because we found that gives us a good enough approximation to the underlying distribution in most practical scenarios. Now, because lines in CDF language correspond to uniform distributions, and because the CDF looks like the line connecting to samples within that segment, this implies that the keys within each segment are approximately uniformly distributed. This gives the keys an inherent hash-like behavior, even though they're not really hashes. They have a sense of ordering, but they have this nice uniformity property that allows us to do range filtering very space efficiently. So let's see how we can leverage that property. First, what we're going to do is we're going to store our samples in a tree. This tree is going to be super small because it's going to only contain 0.1% of the data size since we're sampling every 1,000th key. And because of that, it's actually so small, in fact, that it oftentimes fits in CPU caches. So the only thing that we have to really talk about is how do we organize the 1,000 keys that we have in between any two samples. We do this by designing these data structures we like to call infix stores. An infix store is a order-preserving hash table of compressed keys. That's a bit of a mouthful, so let's dissect that and see what that means. An infix store compresses the keys that it's working with by first removing their longest common prefix. In doing so, we don't actually lose any information because the longest common prefix is already encoded in the tree. It also ties back to how we're able to store more fine-grained information for dense regions of the key space versus sparse regions of the key space. This is because the longest common prefix is longer for dense regions of the key space, whereas it's shorter for sparse regions of the key space. An infix store also removes a suffix from each key to homogenize their lengths. This is where we do actually lose some information, but it allows us to convert our variable length keys into fixed length representations that are much easier to work with. So what we end up with are these patches of bits that we took from the middle of each key, hence the name infix. Because these infixes are patches taken from the original keys themselves, they inherit their original ordering, and they also inherit their uniform distribution. So they look like small, uniformly distributed digests of the keys, which makes them ideal for storage in a hash table. We're going to be able to store these infixes very compactly because of the uniformity. Now, the way that's going to go is we're going to split each infix into an address and a fingerprint. You can think of each address as being 10 bits long because we want to map 1,000 infixes to 1,000 slots in our hash table. And you can think of each fingerprint as being log of 1 over epsilon bits long to guarantee a false positive rate of epsilon. Okay? So the only thing that we have to do is simply store each fingerprint in the slot indicated by its address. In doing so, we're storing the fingerprints explicitly while storing the addresses implicitly because we know the addresses based on the location of the fingerprints within the hash table. So what we end up with is a order-preserving hash table that gives us constant time access. This hash table, again, is order-preserving because the infixes themselves preserve the original ordering of the keys, and it has constant time accesses because the uniformity of the infixes give the same nice load balancing property of hashing. We actually implement this hash table using techniques inspired by the rank and select quotient filter, which was a paper from back in 2017. Okay, so all in all, we have a cache tree in our data structure and a bunch of infix stores. We actually implement our cache tree using a YFast trie, which is a cute data structure from back in the 80s. You can think of this as basically giving you successor search in O of log L time, where L is the length of the key that we're searching for. This is in contrast to traditional tries, where successor search took O of L time as opposed to log L, because we had to traverse the entire trie. So YFast tries give us an exponential speedup over traditional tries. And well, each infix store we argued is constant time, so all in all, we have a total runtime of O of log L for our data structure. So the only thing that remains to be answered is how do we check if a range is empty? We do that by first looking at our query and searching the trie to see if there's any sample included in the range. If there is one, well, the range query is for sure non-empty, so we return a true positive. So the more interesting case is where the query is actually so small, in fact, that it doesn't include any of the samples, which also means that it's fully subsumed by an infix store. In this case, we're able to compress the endpoints of the query in the same way that we compress the original keys of that infix store. This gives us a range query over infixes now, which we're able to handle by doing a short scan over the infixes within the infix store. In particular, if we find an infix that is strictly in between the endpoints, we can actually return a true positive. The reason for the answer being a true positive is that, well, the infixes were order preserving. So if we find an infix that is strictly in between the endpoints, the original key must also have been strictly in between the query endpoints. So the answer must be a true positive. If we don't find any infix that overlaps with the query range, then we get a true negative. So this means that we can actually only get a false positive when the endpoints happen to exactly match some infix in our infix store. And the probability of this happening is 2 to the negative f, where f is the length of the fingerprints that we're storing. This is because of the uniformity of the infixes in our infix store. Now, this guarantee is a bit different than the guarantees we're usually used to seeing, in the sense that it's not a worst case guarantee on the false positive rate, it's a semi-robust guarantee, which means that it holds really well for data that comes from a smooth distribution, so things like numeric data we're really happy with, but it holds less well with jagged distributions, like this one you see right here. We have actually observed jagged distributions in some natural language data. What's interesting is we've actually observed that if we apply entropy encoding to compress the input keys before constructing a range filter on them, that is going to implicitly smooth out the distribution and allow Diva to work its magic. We have also seen that even if you compress the keys using entropy encoding, you might end up with duplicate infixes, which in some sense waste space. So a natural approach to addressing this would be to only store one of those duplicate infixes and reuse the space of the rest to store more fine-grained information of the keys and differentiate them. We actually implement these techniques in an extension to Diva we like to call Diva++, which is going to appear in the VLDB journal very soon, so keep an eye out for that. Okay, let's also briefly talk about the evaluation as well. Here I'm comparing Diva to Surf, which is the only other range filter that supports variable length keys, and Memento, which is the only other range filter that supports dynamic updates. Here I'm considering an integer dataset, and I'm varying the range query size on the x-axis, and I'm showing you the false positive rate that we're measuring on the y-axis. As shown, Diva attains a stable false positive rate that's better than the other baselines by multiple orders of magnitude. In terms of query time as well, Diva attains a stable query time while being on par with the state of the art. In terms of variable length keys, I'm comparing Diva to Surf, which is the only other range filter that supports variable length keys. Here I'm varying the space budget on the x-axis, and I'm showing you the false positive rate attained by the filters on the y-axis on a normally distributed dataset. As shown, Diva attains a false positive rate that is better than Surf by multiple orders of magnitude. We also compare Diva to Surf on a real-world English dataset, and we show that Diva attains a false positive rate that is on par with Surf and is also much better when the space budget is more stringent. Okay, so why is Diva so much better than Surf? Surf, for context, is a trie that is truncated just enough so that the keys are differentiable from each other. Because of this, in terms of the false positive rate guarantee, surf actually is really just the best effort attempt at reducing the memory footprint, whereas Diva minimizes the memory while guaranteeing you a bounded false positive rate. In particular, this is because surf forces the differentiation of the keys, whereas Diva learns the dataset's distribution, which allows it to be more smart in what it's storing. Specifically, if we look at what happens within an infix store versus what happens for the corresponding keys in a surf instance, what we see is that Diva is able to implicitly store parts of each key to save space. This is what was happening within the infix store. We were splitting each infix into an address and a fingerprint, and we were storing the addresses implicitly, so we weren't really paying anything for the addresses at all. This is in contrast to surf, which has to explicitly store all of the bytes until it differentiates all of the keys. So it consumes more space in that regard, and it doesn't actually guarantee any sort of space guarantee to us, whereas Diva is able to provide a formal space bound. In terms of speed, well, Diva is using a Y-fast trie, whereas surf is a traditional trie. So the runtime for Diva is going to be O of log L versus the O of L you would get from surf, where L is the length of the key that we're searching for. This is an exponential speedup over surf. And finally, in terms of dynamicity, well, surf is a static data structure because it's implemented as a packed array that you cannot insert into without having to shift the entire thing in memory. This is in contrast to Diva, which slightly over-provisions slots within its infix stores to absorb new insertions. Beyond just over-provisioning, though, Diva employs two other techniques that are of interest to handle dynamic updates. Specifically, it adds samples to its trie over time as we get more and more inserts to maintain an accurate approximation of the distribution. And by adding samples, it's also splitting older infix stores, which are becoming larger and larger, into smaller infix stores. It decides on whether to pick each key as a sample by using a randomized policy. We detail these techniques in our recent submission to SIGMOD Research Highlights of 2026, which we were kindly invited to submit a paper to. Okay. Beyond that, though, the original paper talks about the details of infix stores, how we can integrate Diva into a B-tree-based database to improve its performance, and an in-depth theoretical analysis to ground our work. So if you're interested in any of that, please check out the paper. And with that, I thank you for listening.